Good morning, everyone. Today we are going to discuss an important topic in image segmentation called edge linking and boundary detection. In image processing, detecting edges is the first step. These edges are often broken, noisy, or and incomplete. So our goal is to connect these edges from meaningful structures and identify boundaries of objects. This is especially important in biomedical images where we need to accurate organ or tissue boundaries. Today we will understand how edges are linked and how boundaries are formed from them. Let us first recall what we get after edge detection. When we apply operators like Sobel or Canny, the output is not perfect. We observe edges are discontinuous. So the noise is present. Edges are broken into small fragments. And so instead of clear object boundaries, we get scattered edge points. This is a major problem because such fragmented edges cannot be directly used for analysis. So the next step is to convert these into meaningful structures. Now we do edge linking. Because raw edges are not useful unless they form a complete structure. Edge linking helps to connect broken edges, segments, converted scattered edges into continuous lines, form a meaningful contours. And for example, if we want to detect a tumor boundary, we need to continuous outline, not disconnected points. So edge linking is essential to move from detection to interpretation. Now let us think like engineers. Our goal is to detect accurate boundaries of organs or structures, but we face problems like noise, weak gradients, broken edges. So we need a strategy. The idea is to link edges based on similarity, like intensity, gradient, continuous, smooth connection. So instead of the randomly connecting edges, we apply constraint to ensure meaningful edge linking. Edge linking is based on the important parameters. Gradient magnitude, it is the strength of the edge, and gradient direction, it is the orientation of the edge. Pixel connectivity, it is the neighborhood of the relationship of pixels. If neighborhood pixels have similar magnitude, similar directions, they are likely belong to the same edge. So we connect such pixels to the form to continuous edges. This ensures that linking is logically not random. Logical edge linking works within a small neighborhood, usually into 3 into 3 window. Here we compare difference in magnitude, difference in direction. If both differences are within the thresholds, magnitude differences greater than t and the direction differences greater than alpha, then we connect the pixels. This method is simple and fast, but the limitation is it works only for nearby pixels and may fail for larger gaps. Global edge linking considers the entire image. Instead of local comparison, it uses graph search. Path orientation techniques, it tries to find the best path connecting edge points across the image. This results in better connectivity and more accurate structures. However, it is computationally complex and time consuming. So there are always a trade-off between accuracy and complexity. Hough Transform is a powerful method for edge linking. It is mainly used to detect lines, circles. The idea is edge points is image space are mapped into parameter space. In parameter space, intersections represent a valid space like a line or circle. This method is very robust, especially in noisy condition. So even if edges are broken, Hough Transform can still detect the global structures. Now let us move from edges to boundaries. An edge representation, a local intensity change, but boundary representation, a closed counter separating two regions. So the edge is a local feature, boundary is complete structure. Boundary detection is important because it defines the shape of an object. In biomedical images, this helps in identifying organs or tumors clearly. Once we detect boundaries, we need to represent them efficiently. One common method is chain code. In this method, each boundary direction is encoded as number from 0 to 7. It represents movement between pixels. This provides compact storage, easy processing. So instead of storing all pixel coordinates, we store direction sequences. Boundary following is used to trace a boundary completely. The idea is start from one boundary picture, move to its neighbor. Continue tracing in a consistent direction, usually clockwise. We use connectivity rules to ensure correct tracking. Finally, we return to the starting point. From a closed counter, this gives a complete boundary representation. Boundaries can also be represented using graph models. Here, the pixels are treated as nodes, connections are treated as edges. So the boundary becomes a connected path in a graph. This representation is useful for applying algorithms like shortest path or connectivity analysis. It provides a mathematical way to analyze boundaries. In a mathematical applications, edge linking and boundary detection are very important. For example, in CT scans, we detect organ boundaries. X-rays, we identify bone structures. In MRI, we detect tumor boundaries. These techniques help in accurate diagnosis, treatment planning, so they have direct clinical importance. Now let us look at challenges. We face problems like noise breaking edges, weak gradients, false linking. To overcome this, we apply smoothing to reduce noise, use thresholding to filter weak edges, use hybrid methods combining multiple techniques. So practical system always use combinations of these methods. And let us summarize. Entire concept, we started with the edge detection output, which had noise discontinuous edges. Then we applied edge linking, local methods, global methods of transform. Finally, we moved to boundary detection, closed counters, and region separation. Applications include MRI, CT, and X-ray. So the full pipeline is edge are linked, closed, and interpretable regions. These are the references. Thank you.